Although we found the Hamiltonian for the double average of the problem, average over both the outer binary and the inner binary, let's use what we learned about Hamiltonian dynamics to solve for the motion under this Hamiltonian. So let's use the Hamiltonian equations, and let's use then the Delaunay variables and apply this to this Hamiltonian. So as we discussed, the Hamiltonian does not depend on the mean anomaly. So the first action then, which is related to the energy, is conserved. That means that the semi-major axis is constant. And the third one also, the Hamiltonian does not depend on the argument of the ascending node. Therefore, the vertical component of the angular momentum is conserved. For the second one, though, we do have a variation of J2, which is a derivative of the Hamiltonian with respect to the argument of pericenter. So we're going to have that the variation of the angular momentum is non-zero. So let's take the derivative of the Hamiltonian then with respect to the argument of pericenter. It's only this last term here that has the argument of pericenter. So it's simple to derivate. Let's rearrange this. Now let's equate that to the derivative of the angular momentum. Now the angular momentum depends on the semi-major axis and the eccentricity, and the semi-major axis is constant. So therefore, this is a expression for the time variation of the eccentricity. So now let's take the time derivative of the angular momentum and equate that to the right-hand side. That simplifies a bit. And remember the mu is equal to g times the sum of the masses. Isolating a dot, then we have, notice that gm1a1 cube is the square of the mean motion of the inner binary. And this expression here is the mean motion of the outer binary. And because the vertical component of the angular momentum is conserved, and that depends on the eccentricity and the inclination, you can take the derivative of the vertical component of the angular momentum, it has to be zero. So that is equal to the angular momentum times cosine I. If you apply the product rule here, and because the vertical component of the angular momentum is conserved, this has to be equal to zero. The derivative of the angular momentum, L dot, we already computed. So that's the expression we have in the end. Let's eliminate the constants and isolate I dot. And substituting now the expression that we found for E dot, these two equations for the derivative of the eccentricity and the derivative of the inclination define the cycles of eccentricity and inclination that the inner binary executes under the influence of the outer binary. Here you're seeing these cycles. You have a cycle in eccentricity together with a cycle in inclination. Now you're seeing this noise here superimposed on it. That's because this is an n-body calculation, and the theory that we worked out is for the averaged motion. We average over the motion of the inner binary and the motion of the outer binary. If you compute the n-body, you're going to find that, yes, you have this oscillation superimposed. These oscillations are the motion of the inner and the outer binary, but on top of it, you have the secular motion of cycles of eccentricity and inclination. As the eccentricity goes up, the inclination goes down, keeping constant the vertical component of the angular momentum.